Hello everyone. In the last class, we have started a design problem related to masonry building. We were designing southern wall of a multi-purpose masonry hall. Today, we will take the same problem further, where we shall discuss more into compliance to material specifications and other geometrical as well as support conditions. So, since our building is supposed to be located at New Delhi, which is located in seismic zone 4 and has an importance factor of 1 based on table 2 of IS 4326 2023, the building category is specified as D. I hope you have the copies of IS 1905-4326 ready at your desk for a quick perusal. I have deliberately not added these tables in these slides so that you end up opening your code book and look into these specifications. So, based on this table 2 of IS 4326, we obtain the building category as D. Now, since we are using class 10 brick which has a minimum compressive strength of 10 megapascal, it is adequate. Why? Because for a building category D, as per section 8 of IS 4326 2013, we need to use well burnt clay bricks with minimum compressive strength of 3.5 megapascal in any earthquake resistant construction. So, the class 10 brick sufficiently passes this standard. We have already looked these material specifications in lecture 9.1. Now, related to mortar grade M1 which we have used, this is also adequate for our building category D. For a building category D, based on table 3 of IS 4326, we can use a mortar M1 which has a minimum compressive strength of 5 megapascal. So, this is also complied. So, our material specifications are complied. We are not checking the material specifications related to steel reinforcement, because in a steel reinforcement it is more of a detailing perspective. So, now we will look into compliance to various geometrical specifications related to masonry walls in case of earthquake resistant construction. So, the first criteria which we are dealing with is the total height of the building, which is 8 meters. It is less than 15 meters as per clause 8.2 of IS 4326. The maximum height of a masonry building can be up to 15 meters or up to 4 stories. Further, in seismic zone 5, where your building category has to be E, then your building height is restricted further up to 3 stories only. But in case of this very example problem, where we have the construction happening in zone 4, we can go up to 4 story height or up to 15 meters in height. In our case, the total height is 8 meters, which is less than 15 meters. So, it is sufficient. Here, while calculating the total height, I have assumed that the foundation will be sufficiently deeper, and from the top of the footing up to the roof level it is 8 meters. Otherwise, the wall height is 3 plus 3, 6 meters only. Then, what is the effective height of the wall? Since we are considering the height of the wall in only one story, so the effective height of the wall is found to be 0.75 h, which is 2250 millimeters. Here the value of h is the height of the wall between center of supports. So, between center of the RC slabs. So, that is 3 meters. Now, in this case we have assumed that our RC slab is offering full restraint, that is lateral as well as rotational at both the ends of the wall, at top as well as at bottom. Further, we also understand that since each portion of the wall is having a length which is exceeding 4 times the wall thickness, the wall thickness is 250 millimeters, and as you can see, this is 1200 millimeters, this is 1600 millimeters, this is 2500 millimeters. which is more than 4 times of 250 mm. That's why all of these are classified as masonry walls rather than masonry columns. So we shall follow table 4 of IS 1905 in order to find the effective height, which says it to be 0.75 times of the height of the wall for such a wall which is having full restraint at both ends of the wall. Okay, we have discussed it earlier as well, probably in lecture 9.2. You can go back to those videos as well and have a look. For finding out the effective length, again we will see the support conditions. For a wall as shown over here, which is supported by cross walls, eastern as well as western wall at both the ends, but the wall is not continuous beyond the support. So in such a case, the effective length shall be equal to 1 times of the length of the wall. In this case, the length of the wall is 8 meters. So the effective length is 8000 mm. Then the effective thickness of the wall shall be calculated. Again, since our wall comprises of solid masonry units and we do not have any cavity wall kind of thing, so in this case the effective thickness of the wall shall be equal to the thickness of the wall itself, which is 250 millimeters. Now we have understood that the minimum thickness of walls in case of masonry buildings should be 200 millimeters, and therefore this also follows this guideline based on clause 4.5 and table 6 of IS 4326. However, you can also build masonry walls which are thinner than 200 millimeters, but you need to apply certain additional ductile detailing guidelines into that. We have looked into those guidelines earlier. However, since in our case the wall thickness is exceeding 200 millimeters, we do not need those guidelines. Further on, while calculating effective thickness, we should have also used a stiffness coefficient. In this case, since our wall is being adequately bounded into cross walls, therefore the stiffness coefficient is equal to 1. You can go to table 6 of IS 4326 in order to obtain the value of stiffening coefficient. Now, once we have our effective height, effective length and effective thickness known to us, we are ready to calculate the slenderness ratio. The code defines slenderness ratio as the maximum of the slenderness ratio obtained based on effective height and effective length. It is obtained from clause 4.6 of IS 1905. So slenderness ratio based on effective height is given by effective height divided by effective thickness, which is equal to 2250 divided by 250 equals 9, and the effective length divided by effective thickness gives us the slenderness ratio based on effective length. So this is calculated as 8000 mm divided by 250 mm, obtained as 32. Now the slenderness ratio shall be the maximum of the two, which is 32 in this case. Now in this case the slenderness ratio is violating the limit, which is 27. So we need to revise the wall section because it is a slender wall in this case. Now I believe that the code also mentions minimum of the following, which does not make much sense. So slenderness ratio is the maximum of these two cases. Now while revising, there are a few options. We can increase the thickness of the wall, but that will eat our usable space of the building. So what we will do? The other option in this case, since our slenderness ratio is based on effective length, so this is our governing slenderness ratio. So what we can do is that we will reduce our effective length. How will we reduce our effective length? By providing a pier or buttress at this point. So this is a small cross wall kind of thing, also called as pier or buttress. So this we have provided at 3500 mm from left end and 4500 mm from the right end. So the center of this pier is located at 3.5 meters from the left end and 4.5 meters from the right end. So this reduces our effective length. So our effective length in this case shall be the effective length obtained for this wall separately and for this wall separately. Now since we want to maximize our slenderness ratio in order to have a conservative design, we will take this very wall, and if we take this wall, what you observe that at one end the cross wall is supporting the wall and the wall is not continuous after that, but at the other end the cross wall or the pier or buttress is supporting the wall and the wall is continuous further. Now for checking the continuity of the wall, again you have certain checks, that is it should be at least h by 6 after the cross wall, this very projection. So that is checked in this case. I have checked it and then I have observed that this is continuous. So in this case the effective length shall be 0.9 times of 4500 mm, which is 4050 millimeters. So 4050 millimeters. So the slenderness ratio is now calculated as 4050 divided by the thickness of the wall, which is 250 mm, calculated as 16.2, which is less than 27, which is now satisfactory. So our slenderness ratio is now satisfactory. So what we will provide, pier or buttress which has dimension of 500 millimeter by 250 millimeters at this point. We have also provided a similar pier or buttress at this point in the northern wall as well, because we know that the design will be very similar. Now how have we arrived at these dimensions? One is that I have also made sure that these geometrical parameters which are constants given in IS 4326 are also satisfied. We will see how I have made sure that they are satisfied related to pier or buttress in the upcoming slides. Before we get over there, let us also check the load eccentricity. So what is the load eccentricity in this case? Since our reinforced concrete slab is spanning 12 meters in this case as shown over here, which is exceeding 30 times the wall thickness. What is 30 times the wall thickness? 30 into 250 millimeters. So the span exceeds that, so it will be classified as a not normal span. So in this case the design eccentricity shall be considered as 1/6 of the wall thickness. So the design eccentricity is 1/6 of wall thickness, which is 41.67 millimeters, or the design eccentricity ratio, which is the ratio of design eccentricity to the thickness of the wall, is equal to 1/6. Now this is based on guidelines presented in appendix A of IS 1905, which says that if your RC slab has a span which is exceeding 30 times the wall thickness, the design eccentricity ratio you can consider it to be 1/6, or the design eccentricity you can consider 1/6 of the wall thickness. If the span was smaller than 30 times the wall thickness, then in this case we could have taken eccentricity to be 0. However, the design eccentricity is best found out based on judgment of the structural engineer. However, guidelines given in appendix A are well and good, and you should be able to follow them. We have discussed all those guidelines earlier. Then let us look into compliance to various lateral supports. In our case, the slenderness ratio has been found to be 16.2, which is all right. Now let us check the support, that is the cross walls or piers. Here we have two cross walls at the either end, one at either end, and you have one pier or buttress over here. So in this case the code IS 1905 says through clause 4.2.1 that the minimum thickness of such cross wall or pier or buttress shall be equal to half of the supported wall thickness or 90 millimeters, whichever is larger. Now our supported wall is 250 millimeters thick. So in this case our pier or buttress or cross wall should be minimum 125 millimeters thick. Therefore we have provided the pier buttress which has thickness of 250 millimeters, it is sufficient. Now, what is the minimum length of the wall, cross wall or pier or buttress that you need to provide? It is equal to 1/5 of the wall height. So, our wall height is 3 meters. So, it shall be minimum 600 millimeters. So, these cross walls, as you can see, if you reduce 250 from 2000, this is 2000, if you remove this very wall thickness, the supported wall, then still it is larger than 600 millimeters. So, these cross walls are sufficient, and we have provided the buttress or pier which has also length of 600 millimeters. So, this makes this also adequate. So, therefore, our provided geometry of pier, which is 600 mm by 250 millimeters, is sufficient. Now, let us look into some more details related to these cross wall or pier or buttress, which is related to the thickness and spacing of these stiffening walls. So, if you are stiffening any wall, that is the wall to be supported has a thickness of, let us say, 25 centimeters, because this is the wall which is being supported or stiffened. So, this wall has a thickness of 25 centimeter. So, for 25 centimeter thick wall, the height of a story should not exceed 3.3 meters. Right, I am interpolating between these two values. Our story height is 3 meters, so it is adequate. The stiffening wall on the other case, for 1 to 3 story building, shall be minimum 10 centimeter thick, which means 100 mm thick. We have provided 250 millimeters thick. So, this is all right. Then the maximum spacing of these walls shall be 7 meters. As we can see in this case, I am interpolating between 6 and 8, because our thickness of wall to be stiffened is 25 centimeters. So, 7 meters. Here the spacing is much lower, it is 4.5 meters on this side, and on this side it is 3.5 meters. Further, we also satisfy the maximum height to width ratio. In our case, what is the maximum height of the wall? Considering both the stories, it is 6000 mm and width is 8000. So, the height to width ratio is equal to 0.75, which is okay if you look into the clause 4.2.2 of IS 1905. So, that is how we have been able to satisfy various constraints related to our lateral supports. Now, let us look into other geometrical conditions such as those shown over here. These details are given in table 4 and figure 7 of IS 4326. I suggest that you open your code now and look into that. These two items, that is table 4 and figure 7, have to be read together, which means that the detailing is provided over here in table 4 and figure 7 shows it in a schematic manner. So, what do we need to check over here? Let us see one by one. So, the distance B5 from inside corner of the outside wall. So, from inside corner of the outside wall up to the opening. So, this is the distance B5, as you can see in this figure, distance B5. So, in our case, that is 2250 here, here it is 950. What is the minimum that you need to have? For a building category D, you need to have minimum value of B5 as 450 millimeters. So, this is satisfied. It is from the outside wall. So, this very value, which is 375, does not violate this, because we are talking only from the corner of the outside wall. So, this very value 950 and this very value 2250, both of them are satisfying this very criteria. Then the total length of openings, that is the ratio B1 plus B2 plus B3 divided by L1. What is this? For any wall, B1 plus B2 plus B3. Then this is a cross wall or pier or buttress. Then in this case B6 plus B7 divided by the length of this wall, that is L2. So that is mentioned over here. So here we can calculate that. So it shall be equal to, again 1200 is the opening in this case, and from here to here we shall again calculate that. You can check on your own. I have deliberately not put those values over here so that you take your time, you check whether it satisfies or not. I am telling that it is satisfying a specified the geometrical conditions. Again in this case the total length of openings is 1.5 meters and this is roughly 4,500. So all of these values, both of these values are actually lower than 0.42, which is all right. Why we are considering 0.42? Because our building is a 2-story building and the building category is D. Okay, the next thing which we need to check is the pier width between consecutive openings. So these two are our consecutive openings and the pier width shall be minimum of 560 millimeters. In this case it is 1.6 meters. So this is also completely fine. Then the vertical distance between two openings, one above the other. In our case we do not have such condition. We do not have any two openings above each other. And even if you consider vertical opening, that is doors in ground story and first story, again those two have sufficient distance between each other. Then width of opening of ventilator, we do not have our ventilator in this case, but if we want to open any ventilator, the width cannot be more than 900 millimeters for a building category D. So we have been able to satisfy all these geometrical conditions specified in table 4 and figure 7 of IS 4326. All these criteria required for good seismic behavior, that is stable behavior during earthquakes. Now at this point I am not saying that our building satisfies all these criteria, because I am only dealing with this wall. I can tell the same for the northern wall because I have also provided the pier or buttress there, but I cannot say that for these two walls. I have not checked for them. So maybe as an exercise you can check for these two walls as well. So in this class we have been able to check the compliance of our building, or particularly the southern wall of the building, for material specifications as well as support specifications. In the upcoming class, which will be the first class of the upcoming week, we shall take into consideration the permissible stresses and the design action in the wall. Then we will also see compliance towards various ductile detailing provisions related to steel reinforcement and some other seismic strengthening measures as well. Thank you.